Hello, this is Concrete Path, and the lecture for your pre-stress concrete is that we call as cracking moment, cracking moment, cracking moment. So this is your cracking moment. This is your cracking moment. Okay. So what this means, I would say you are applying some dead load, live load on the beam. So there is some dead load, there is some live load. That's the final stage. That is the service stage of this beam. So you're applying those because of these we have some top compressive bottom tensile M all by Z, M all by Z. So because of the stresses that is tensile at the bottom, so on the bottom, that is from the soffit side of the beam cross section, we're having some tensile stresses because of this. So that means concrete is in tension. Concrete is in tension. So there's a chance of cracking. There's a chance that cracking would get developed. That concrete is going to crack. And now because of that, now we had to apply that what you call as prestress force. We apply that prestress force at some eccentricity such that its stress is that bottom it develops bottom stress that is compressive, and its eccentricity also develops compressive stress at the bottom, but that's PE by Z. So because of these two, that is because of the P and its E, is try to counteract the effects of those tensile stresses at the bottom. So but there is a chance that net value can be, there's a chance that there might be some chance that net value can be still less than 0. That means net value can still be tensile. So there's chance that cracking is going to be developed. So there I would say there should be a particular value of the moment you're going to apply such that there's no cracking in the concrete. I would say your cracking of the concrete starts at flexural that stress that we call as modulus of modulus of rupture. That is the flexural strength, flexural bending strength. That was your beam was there. You applied the loads, and it was there FCR, and we know the direct relation that that codal provision, that is FCR is 0.7 root FCK. So we have to say that your tensile stresses should be such that they are less than this value. That means if you are going to allow this much amount of stress in the tensile zone, so your cracking might not get developed. So this is, I would say, critical condition for that tensile stress, that I would say your tensile stresses should not be more than FCR, in terms of magnitude. I'm saying, if you got the value of FCR, say you have FCK equals to M25, so your FCR is 3.5 megapascals, but this is tensile stress, so your stresses should be more. It should be less as compared to this one, but in terms of magnitude, we are saying it should be less. So your stresses can be either you should allow only stresses in this zone such that they are less than this or equal to this. So your stresses can be either 3.4, 3.2, 3.1, or it can be also positive side. It can go to the positive side also, compressive side. So we have to ensure that at this condition, I had to apply a moment. Some critical moment should be there. Such that your tensile stresses is equals to flexural strength of the concrete. That means at that critical location, your cracking of the concrete is going to start. So that cracking moment, we can call it as MCR. So this is your moment applied. This is moment because of the all loads, because of dead load and live load. I had to apply that particular value of moment such that would cause that cracking of the concrete. So that we call as cracking moments. Let's write that MCR. MCR is that moment. This is the moment applied because of the external loads. Moment applied because of external loads. So your external loads, we are saying that's because of the dead load and because of the live load, which would cause stresses, tensile stresses equals to flexural strength of the concrete. Flexural strength of the concrete. And that we know that is equals to, I would say, your FCR at the rate of which FCR is equals to 0.7 root FCK. That's equals to your tensile strength for the concrete. So you have to apply this amount of moment such that it can cause that tensile stress equals to FCR. So let's take that what you call as. So this is all about final stage, because we're applying moments because of all those loads, dead load, live load. So it's talking about that transfer stage, that final stage of the stress analysis. So it's talking about final stage of stress analysis. Now, if I take a section that, if I take a general cross section, I would say we have some neutral axis, and there's some force of P applied, P not applied at some eccentricity of E, and this is your final force. I can write this as Kp naught. So your stresses would be Kp naught by A, and here we have top tensile, bottom compressive. So this is Kp naught E by Z top, and this one is your K P naught E by Z bottom because of the effect of P and E. Then third one is that top compressive, bottom tensile, because of all those loads divided by Z bottom. This is M all by Z top. So I had to say that my condition is that I am allowing some value of tensile stresses at the bottom. I'm allowing some tensile stresses at the bottom, and that value is equals to FCR. This value is equals to FCR, that is 0.7 root of FCK. This much amount of tensile stress I am going to allow in the concrete, such that your concrete is also going to utilize, but without going to crack, and your steel is also going to utilize. So that's the condition here, critical moment. So this value is equals to FCR. Okay, this is the condition we have to get, resultant of these. There is some resultant of these. So let's take that after we got it. Okay, after we got it, so I would say, let's say what we are going to talk about. Let's talk about what we are going to say. Okay, FB equals FCR. Yeah. So if I say that bottom stresses, if I calculate stresses at the bottom, I would say this is Kp naught by A minus Kp naught E by Z bottom minus M. Is it positive? It should be positive. This is positive, and the third one is negative. M all by Z bottom, and this should be equals to FCR. Why FCR is negative, so we have to use the sign also, minus times FCR. So it should be tensile stresses FCR. Then we say that by the definition that your actual moments, the moments you are applying, that's all moments, we can call it as M all, those should be less than cracking moments, because I don't want cracking of the concrete. Your moment that contributes to cracking is the actual moment. So your actual moment should be less than the cracking moment. So there should be some particular value of cracking moment that I had to ensure that my moments, external moments, are less than that critical moment, cracking moment. So this is the condition for no cracking, for no cracking of the concrete in the tensile zone. For no cracking, I would say your FCR should be less than your stresses in the tensile zone. Tensile zone, that should be less than FCR. It should not be more than this. It should not be more than FCR, such that your cracking is not developed. Okay, so let's take that what we call as, let's say that what we call as a problem, and we have to say what is the factor of safety. So the problem is that we have to find the factor of safety, get the factor of safety against the cracking, and concrete is that we have M50 concrete. M50 concrete is there. So what is factor of safety? We have not defined factor of safety, that we also can call this is load factor. So there is a factor of safety. Its factor of safety is equals to, because our cracking moment is more, so I would say this is cracking moment divided by actual moment. Or we can also call it as load factor, or we can say this is factor of safety. Let's say this is factor of safety, and it should be greater than 1. It should be greater than 1, such that no cracking is going to develop. So your problem is that get the factor of safety for the M50 concrete. Your M50 concrete. What is the problem we have? So problem is that problem is the same that's previous problem we have. So this was your previous lecture. This was in the previous lecture that we had one of the beams. One of the beams we had this section. We have all the stuff that we have calculated from this one. All the stuff we have calculated from this one. So we have to take those values for your calculations. So I would be calculating for the final stage. I'm going to calculate for the final stage because we have to take all those moments. That means we have to calculate for the final stage of the problem. Let's take that. I would say you had this section. Okay. You had this section. You applied those moments. You had some moments. M live plus M all. M live plus M dead. That contributes some moment of M all, and that we have also already calculated. You have sum of those two. So your moment, that's all moments. This is sum of this one and this one. So total moments we have. Total moment is coming out to be equals to. Total moment was equals to 2250 kilonewton meter. So this is the moment we have all moments. So all those external moments, that is 2250 kilonewton per kilonewton meter. Okay. And we are applying that eccentricity. We also know there is some eccentricity of 500 millimeters. We have this cross section of 100 cross that. All that stuff, we are going to use that. So let's try to remove this stuff. Okay, let's try to remove this stuff. So we need to get factor of safety for M50 concrete against that cracking. So I would say, what is the flexural strength? Can you tell me what is the flexural strength of F50 M50 concrete? Is that 4.95 megapascal? Is that 4.95 megapascal? So I have to say your stresses in the tensile zone should be less than this value. It should not be more than this value. So 4.95 megapascal. So I'm going to solve. See, this is your moment. That is, I would say, this is your working moment. This is your working moment. That's your service stage. Because at the service stage you had some particular value of live load and dead load. So this was your service stage. So I would say this is your working moment. Accordingly, I would say this is your working moment. Now I need to calculate that critical moment. I need to calculate that critical moment that we call as cracking moment. So I had to calculate that at what critical value of moment your stress in the tensile zone is equals to FCR. So I have to calculate that critical moment, or we can say cracking moment, at the rate of which your tensile stresses in the concrete is final value of 0.7 FCK. So that we need to calculate. So I would say in the final zone, in the final stage, because we are talking about the final moments, so your stresses we have to calculate for the final stage. So we're going to calculate for the final stage, that we can say this is your working stage or this is your service stage. So let's try to get that. I would say you're applying some load of P at some eccentricity from the neutral axis such that your stresses are having that value of P by A, and one more is there. That's stress at the top is stress. We are calculating stresses at the bottom because for the final stage your stress diagram is somewhat in this fashion. This is your final diagram of the stress that's at the final stage. So we are calculating for the stresses at the bottom fibers, and this value is P naught. Yeah, it should be P final. It should be P final, final force, PF. PF E by Z bottom. And third is because of the cracking moment. Because of the cracking moment, we have positive tensile, positive and negative. MCR by Z bottom. So where your MCR is because of dead load and live load. But this should be the critical value. We are calculating for the critical value at the rate of which your final resultant stress diagram is in the tensile zone. We have some value of FC or equals to 0.7 root FCK, and this is negative value. And at the top side we can have any value compressive. So our concern is that on the bottom side we have to worry about the bottom tensile stresses. Okay, this is the final stress diagram. So we need to calculate for the critical moment. So let's solve for that. I would say, what is the final force we have? This was the final force, K times P naught. Based on the losses, we have 15% losses. cable area, steel area was provided to you. So, everything is there, and we had that initial force of 4800 after the losses have accounted. So we have 4080 kilonewton. 4080 kilonewton. So I would say 4080 into 10 power 3 newtons divided by the area of the cross section. Area of the cross section we have area of the cross section that was 800,000 millimeters square. 800,000 millimeters square. This was your area of the cross section. So we are calculating stresses at the bottom, because our critical condition for the final stage is that at the bottom there should be some tensile stresses. So this is your F bottom. After that we have plus P final. Eccentricity is 500 millimeters. 500 millimeters divided by Z bottom. Your Z bottom is I neutral axis. So 9.867 10 to the power 10 millimeter power 4 divided by Z bottom. That means divided by Y bottom. Your value of Y bottom is 700 millimeters. You can see from the diagram. 700 millimeters. This is your Y bottom. And this should be equals to, yeah, we should add one more thing. We have to add that MCR. So there's some value of MCR divided by that section modulus. Z bottom is 9.867 10 to the power 10 divided by 700 millimeter power 3, and this should be equals to, and the net value should be equals to minus times 0.7 root of FCK. So this should be negative because we are saying this is the tensile. Net value should be tensile. Negative. Net value should be tensile, negative value. So after calculating that, you would say this is your megapascal. So finally your stresses, your cracking moment is coming out to be equals to cracking moment of 3456.55 kilonewton meter. This is your cracking moment. So we need to calculate the load factor, or we can say we have to calculate factor of safety for that concrete against the cracking. So our factor of safety is cracking moment by actual moments. That's working moment, your actual moments. So your cracking moment we got 3456 kilonewton meter, and divided by actual moments what we have on the working stage. That is the working moments we applied on the beam. Working moment was sum of these two, dead load plus live load, 2250. So your factor of safety is almost 1.5. 1.536 is your factor of safety. So let's take that one more. Let's take one more problem. We have a cross section. We have this cross section of the beam. That's simply support beam with the live load. Live load is there, 6 kilonewton per meter live load, and the beam is having length of 6 meters. And the cross section of the beam is rectangular with the steel area provided. At the top, we have 3 bars, and from the top distance is what we call as 25 millimeters. And we have a few more bars. At the bottom. Add some eccentricity from the bottom, that is 65 millimeters. I would say at the bottom we have how many number of bars? We have 15 number of 5 mm bars, and at the top we have 3 number of 5 mm bars. Okay, and the total depth is 300. Total depth of the beam is 300 millimeters, and the width of the cross section is 200 millimeters. I would say if I use the concept of nominal concrete section, if I approximate that neutral axis is at midspan, if I ignore the area of the steel, so I would say neutral axis is here. So your eccentricity E1 would be this one. Let's say E1 would be equals to 150 minus 25, that's 125, and your eccentricity E2 would be 150 minus 65, that's 95, 85 millimeters. So this is your E1 and E2. That means some P1 force is acting here, some P1 force is acting here, and some P2 force is acting here on the cross section. So we need to calculate the stresses. Okay, we got the right diagram now. Let's talk about the problem. So we have to calculate First part of the problem is that calculate stresses in concrete, stresses in concrete, stresses in concrete at extreme fibers, at extreme fibers, at extreme fibers, at the midspan section, at the midspan section, because of the because of the P, its eccentricity, and because of the own self weight, I can say self weight. So that means it's talking about the transfer stage. What does this means? This means the transfer stage. Can we say that this is all about transfer stage? Transfer stage, can we say that? This is talking about transfer stage. Let's try to have those stresses at the transfer stage. P, E, and self weight. So let's calculate the self weight. What is the self weight? We can have dead load. Self weight is there, WD, that's 24 kilonewton per meter cube into cross section of 0.3 into 0.2, that is dead load of 1.44, and the moment contributed by dead load is WD L square by 8, so moment D is equal to 6.48 kilonewton meters. And I would say live load moment would contribute, live load moment is contributing, let's keep it as it's for now. For the first part of the problem, we had to calculate stresses because of the extreme fibers, because of this PE and self weight. I would say you are having some section and you are applying some P1 force and P2 force at different eccentricities from the cross section. So I would say there is some force of plus, let's say there is some force of P1 by A, and there is one more force that we can say that's P2 by A. That's because it's compressive. Both the forces are compressive and they are direct compressive stress. So this is sum of P1 plus P2 by A. And after that we can say there's effect of P2. P2 is having effect that is hogging moment. So diagram is as that of a previous one. So hogging tensile top, bottom compressive. So this is contributed by P2, E2 by Z. Because your section is symmetric, so we can take Z value as same. So I would say P2, E2 by Z. And because of the P1, it's above the neutral axis. It's above the neutral axis. That means it contributes sagging moment. So this is, we can write this is sagging, and this one contributes hogging. So that's because of that your diagram would be reverse of that. Diagram would be reverse of that. So this would be P1 E1 by Z, and this is also P1 E1 by Z, and this is positive and this is negative. And because of the self weight we have to calculate. Because of the self weight we already know top compressive, bottom tensile. M dead by Z. M dead by Z. So let's calculate those stresses at the top and bottom. So can you tell what's the value of P1 and P2? So your P1 is equals to how many bars we have? 3 number of bars, pi by 4, 5 square into what is the stress in the steel? Let's say stress in the steel is equals to 840 megapascal. This is the initial stress in the steel wires. Initial stress in the steel wires. Okay, that we can say this is multiple of that. So your P1 is equals to P1 force is 49.48 kilonewton. 49.48 kilonewton. And second force is there. Second force is P2, and that is what you can say 247.4 kilonewton. So this one is more, P2 is more, P1 is less. Let's calculate the stresses now. Okay, I would say what is the stresses at the top? What is the stresses at the top? That is P1 plus P2 divided by A. P1 plus P2 divided by A. So I can write 49.48 plus 247.4 divided by the area of the cross section, that is 0.2 into 0.3. 0.2 into 0.3. This is in units of kilonewton per meter square. And second stress is there plus, yeah, I can say stress is at the top. This is negative. I can write negative P2. Your value of P2 is 247.4 kilonewton into eccentricity is 0.085 divided by section modulus is 0.2, 0.3 square by 6, BD square by 6. And third stress is positive. That is because of the load P1, because of the P1 prestress force P1. That's 49.48 kilonewton into that eccentricity of that's what is the eccentricity E1? That is 0.125 divided by section modulus of BD square by 6. And after that we have the dead loads. Because of the dead load we have stress of positive M dead by Z. Your dead load was how much moment contributed by dead load? So 6.48 is the MD, 6.48 kilonewton meter. 6.48 divided by section modulus of Z, BD square by 6. BD square by 6. So that's your stresses at the top. Stresses at the top is coming to be equals to 2.16 megapascal. And we need to calculate stresses at the bottom. Stresses at the bottom. F bottom would be this is same. After that we have positive. So this part is positive. After that we have this part negative, so negative. After that final value is also negative. So final value is negative. So final value is negative. So I have to have here a negative value. So finally your stresses would be data is same except the sign gets changed. So that value is coming to be equals to 7.74 megapascal. So this is your first case. That's your first stage of the stress analysis. 2.16, 7.74, both are compressive stresses. Now we need to calculate stresses. Now second part of the problem is that calculate the stresses. It's saying that get the maximum compressive stress, in the concrete. If there is some UDL also there, UDL of 6 kilonewton, UDL is there, and yeah, so that means there is some UDL also. So that's talking about the final stage. So it's talking about the stresses in the concrete in the final stage. That's the effect of all those loads, P, E, M dead, M live, all those effects we have to take. That is the final stage. So if there is mention of losses, so we have to take the losses also. If there's no mention of losses, we don't have to take the losses. I would say there is no mention of losses. I think there's no mention of losses. If it is not mentioning the losses, so I don't have to say this is final stage. So I can say that if it is talking about the taking the effect of UDL, and it's saying that no mention of losses. If there is no mention of losses, that means we can ignore the losses. If we ignore the losses, so we can directly solve based on the initial P force. We can ignore the losses. We can write here. We can ignore the losses, but still we can calculate the effect of P, E, M, D, M live. That is similar to that of a final stage, but without taking the account of the losses. So second part of the problem is that get the maximum compressive stress in the concrete. So I would say your second stage would, besides that, you have one more stress diagram that is contributed by that live load. That's contributed by the live load. M live by Z. Can you tell me what should be on what side the compressive stress can develop based on the addition of that live load? Can you tell me what should be the net tensile stress, net compressive stress that can develop? Is it at the bottom or is it at the top? Because of the addition of the live load, it's adding negative. That means at the bottom there is a net final diagram might be some sort of in this way. Some sort of diagram would be in this way. So maximum compressive stress would be at the top. So we have to calculate what is the stress at the top in this final stage for these set of loadings. So since we have to ignore the losses, if I ignore the losses, that means your stress diagram is not going to change. Your effects are not going to change. Your P would remain as it is. P1, P2 would remain as it is. So stresses at the top would remain as it is. So this is your first value. After that we have negative value. This is also same. After that we have one more value. This is also same. After that we have one more value. That's because of the moments. That's also same. So one part we have to add. That's because of the live load. Because of the live load we have to add one part. Because of the live load we have to add one more part. So stresses at the top is positive because of the live load. Positive live load. What was the value of live load? The value of live load was that 6 kilonewton meter. So your moment contributed by that is WL square by 8. So that's 27 kilonewton meter. 27 kilonewton meter. That's 27 kilonewton meter. So I can write 27 kilonewton meter by BD square by 6. So final stresses at the top, that's in the maximum compressive stress fiber. That is the maximum compressive stress fiber here at the top fiber. So that stress is what we have 11.16 megapascals. And still, if you want to talk about the bottom fiber, if you want to talk about the bottom fiber, the stress is coming out to be minus 1.26. So final stress diagram is same as I have drawn here. So minus 1.26 is there, but where our main problem was that get the maximum compressive stress, that is 11.16 at this stage of loading. And now the third part of the problem is that get the you have to calculate what you call as load factor, or we can say calculate the load factor, or that is the factor of safety. Calculate the factor of safety against cracking. For that, we have modulus of rupture of concrete. I would say modulus of rupture for the concrete, that we can say this is flexural strength FCR, that is 6.5 megapascal. So for this value of 6.5 megapascals, I had to calculate the factor of safety. That means I had to calculate a particular value of cracking moment, that is because of the dead load and because of the live load. So that value of MCR I had to calculate such that your stresses at the bottom fiber, that is equals to FCR. So let's calculate that MCR. I would say your value of P is going to remain as it's this is also same, but the last part is that we have to remove these two we have to remove, and we have to make one single diagram for that. I would say there's some moment, top compressive bottom tensile, that's equals to MCR by Z. So I would say the final stresses at the bottom should be such that stress is equals to the final stress diagram is such that your stresses at the bottom is equals to tensile FCR. That value was given to you as 6.5 megapascal. So I had to equate that equation with that value of minus 6.5. So I would say there is some value of minus 6.5 at the bottom, at that bottom fiber. That's minus 6.5 megapascals at the bottom. So I need to calculate for that particular value of MCR. So this part we have to remove. So I would say there's some value of MCR such that the final stresses at the bottom fiber is equals to minus 6.5 megapascal, that is tensile. So all the data is same except that your MCR is going to change. So you can solve that MCR is going to be equals to cracking moment is coming out to be 49.4380 kilonewton meters. Now, what was the actual loads? What was the actual moments we had because of the dead load and live load? Dead load and live load contributed how much moments? 6.48, 27. So 27 plus 6.48, that is 33.48. Yeah. So I can say your factor of safety would be 49. Is it 49? 49.4380 divided by 33.48. So factor of safety is equals to 1.476 against the cracking of concrete. Okay. This part is also over. So let's pause for some time. Okay. Let's go for one more problem. Let's take one more. You have this PSC beam, okay, with this cross section, that is I section 100. Okay. So then the width here is 100 and top width is also 100, and the thickness of the flange is 70. This one is also 70, and we have placed the steel bars at the top and at the mid. So we have placed 3 bars at the top 3 bars at the top, and they are at 35 millimeters from the top. And similarly, we have placed it 6 bars from the bottom, 6 bars from the bottom in this way. 1 2 3 4 5 6, and the distance of them is equals to, this one is your 20. After that we have 30 center to center. After that we have 20, such that I would say that okay, this is 70, and we will say these are your 6 bars, 6 bars of 4 mm diameter. And similarly, these 3 bars are of 4 mm diameter phi. Okay, and the stress in those bars, initial press stress in those bars is 800 megapascal. Okay, this is your 50 millimeters width of the web, 50 millimeters, and the depth of the web is 100 millimeters. And if this is symmetric, and we are going to ignore that, what you call as equivalent cross section, so I'm going to say neutral axis is at the midspan, at the mid part, at the mid depth, I would say mid depth. So neutral axis at the centroid. So this is our neutral axis. So I would say we had some E1. I would say we have some E1. We have some E1 equals to, total is 170 up to the top. Total is, I would say, 50 plus 70, 120 up to the top. So this would be 120 minus 35, and this would be I would say up to the junction, that would be 50, and after that we are having 20. That means 70 plus 15, 70 plus 15, 85. It should be 85. This part should be E2. That is 50 plus 20 plus 30 by 2. That's 85 millimeters. And we are having some Prestress force P1 and P2. So we can solve P1, P2. So P1 would be equals to 3 bars of pi by 4 square into that 800. And P2 would be 6 bars of pi by 4 square into 800. And P1, P2 would be equals to, your P1, P2 equals to, I would say, P1, P2 equals to, P1 is 30.16 kilonewton, P2 is 60.3232 kilonewton. Okay, so these are your stresses. See, these are your Prestress forces, and we need to say the problem is that get the sagging moment. What should we apply? That should we apply it such that our maximum compression stress in the concrete is 14 megapascal, and maximum tensile stresses in the concrete is that is 1.4 megapascal. This is negative value. I can say this is negative value. So also, where it's mentioned that neglected the losses because of those that we have the losses. So we had neglected those, and it's saying that what's the moment we can apply. So it's talking about actually final stage, because the M, that can be because of the external moments. So I have to take that final stage corresponding to no losses, and thereby we can solve for that particular problem. I can solve first the moment of inertia about the neutral axis. I would say that it's 100 into 100 plus 2, 140, that's 240 cube by 12 minus smaller rectangle of that dimensions 50 into 100 cube by 12. This is your INA. That's 111.03 10 to the power 6 mm power 4. And Z we can solve that is, because of the symmetry, I would say Z is equals to I by 120, because Y top equals to Y bottom, Y equals to 120. So Z would be equals to 925.27 10 to the power 3 millimeter power 4. Okay, now we need to calculate the stresses at the top and at the bottom. So I would say that we are having this section. We are applying a force of P1 at some eccentricity of E1, and we are applying one more force, that's P2 here somewhere at the mid part of this. So that's P2. So that's at eccentricity of E2. So I can solve the stresses now. I can take the stresses now. I would say this is your P1 plus P2 divided by the area of the concrete section. After that, one more is there. Because of the effect of P2, I would say top tensile, bottom compressive. P2, E2 by Z, negative, positive. And because of the third moment, that is sagging, because effect of the P1, sagging effect of P1, E1. So I would say top compressive, bottom tensile. That is P1, E1 by Z. And because of the dead load, I would say because of the total dead load plus live load, contribute to this moment MA, that we can write that as MA, top compressive, bottom tensile, MA by Z, and this is also MA by Z, such that the resultant should be such that our stresses at the top, because we are talking about the final stage, that means final stage diagram is somewhat in this way, ideal stress diagram. But according to this condition, our final diagram should be that we're having some compressive 14. After that, we are having some tensile of 1.4. So diagram should be in this way. So final diagram should be some sort of this way. Let's form that final diagram. So this is our final diagram, and this value is 1.4 megapascal negative, and this is your positive 14 megapascal compressive. So let's solve for that. All the data we know, we only have to get the moment. What should be the moment we have to apply? So I would say, based on this condition, can I say that we have only one unknown? Can we say that we have only one unknown, but we can have two equations? Can we see that we have only unknown, that's MA, but we have two different equations, that's F top and F bottom, two different equations we have. So I would say that MA should be the lower of these two values. So let's try to get from one of the equations. Let's try to calculate from one of the equations. I would say F top is equals to P1 plus P2. So substitute the values of P1, P2, where we have P1, P2. So I would say P1, P2, we would be solving that, and P1, P2 is equals to one of the value is 30.16, second value is 60.32. So divided by the area of the concrete section. So area of the concrete section we can directly solve now. This is your section, and its area of the concrete section is, cross section is that, let's try to have that value somewhere. So that's 100 into 70 plus 50 into 100 plus 70 into 100. So that value might be somewhere. So this is your area of the concrete section. This is your area in the millimeter square. Let's say this is your area, and you know that. Okay. After that, second one is your stress at the top, that is tensile, that negative, that I would write P2. What is the value of P2? P2 is your 60.32. P2 is bigger because we're having more number of bars at the P2 side, so your P2 is more, 60.32. Eccentricity E2, that's 85 millimeters. I can write 0.085 divided by section modulus of, and section modulus we have calculated somewhere, that is 925.27, 10 to the power 3 millimeter power 3, it should be millimeter power 3. Okay, this is your section modulus. After that, one more is there, effect of the P1. So that's positive at the top. So P1 is only 30.16, and eccentricity of the P1 is 120 minus 35. 120 minus 35 means 85. So this is also 85. Eccentricity E1 is also 85. So 85, 0.085 divided by section modulus 925.27, 10 to the power 3 millimeter power 3. And you have to ensure that what is the units you are keeping. What is the units you are keeping there. So you have to ensure that all units are correct. And after that, we have some moment. We had some moment that we need to calculate. Let's say there is a moment of top positive. So I would write some moment positive MA by section modulus of 925.2710 to the power 3 millimeter power 3 is equals to some stress that is 14 megapascal. That is some 14 megapascal. 14 megapascal. So you have to convert the units feasibly and accordingly, and you can get the moment MA that comes to be equals to minus 11.11 kilonewton meter. So 11 means negative, means that you don't have to apply sagging moment. You don't have to apply sagging moment because our stresses have been here calculated as per that M was sagging, but we got negative value. That means we don't have to apply sagging, but we have to apply hogging. But question was mentioning that you have to calculate sagging moment, so it does not make any sense. So this problem does not make any sense. This is not making any sense. If we want to calculate sagging, so we got negative value of hogging, so it's a value of hogging we have to apply there. It's a hogging moment we have to apply there. And one more thing is there. One more thing is there that we need to check. That's second stress. Stress at the bottom. Stress at the bottom would be same. Stress at the bottom is same, that is P1 plus P2 by A. This part is same, P1 plus P2 by 2, that is same. So I would write this is same plus. After that, this part is also same, but we have to keep it positive. So this part we have to keep it positive. After that, this part is also same, so we have to keep it negative. After that, this part is also same, but we have to keep it negative. So negative. And finally, we have to equate it with minus 1.4 megapascal. So from this equation, we can get that second condition for moment applied should be, that's moment because of all those dead load, live load, that is coming to be equals to 8.625 negative kilonewton meter negative. So I would say the moment that should be applied, is that minus moment should be applied. It should be minimum of those two conditions, that is minus 8.625 kilonewton meters. If you apply that 11.11, that is safe for the first condition. You are achieving 14 megapascal, but you might be having some different value of 1.4 here, so you won't achieve this value thereafter. So your values should be lesser than these values. Okay, let's go for the final part of the topic. That's called as, that we call as Kern points. Okay, Kern points. Let's say that you had that general cross section. There was a beam with some UDL, dead load, live load, and you calculated moment all. Okay, and there was some load, there was some P force acting somewhere at some eccentricity, and you calculated those stresses P by A, and you also calculated those what you call as PE by Z, and after that you calculated M all by Z, and after that there was some resultant of those. Some diagram can be there. Let us say that diagram is somewhat in this fashion. Let's say the final diagram is this one. Let's say this is our final stress diagram. Okay, it can be any other thing. So we are saying that this is our final stress diagram, and from that, can you say how can you calculate the C force? I would say C force would be somewhere here, and the C force is always equals to P force, and that C force was, we calculated that as average stress into area of the cross section. Did we calculate that as average stress into area of the cross section? And I would say the centroid was somewhere here at some y bar, such that I said this is your f top, this is f bottom, such that your y top is that from the top, your centroid of that location of the C force is f top plus twice f bottom divided by f top plus f bottom into that d by 3. This was your location of the y, that C force. Now there are two different possibilities of that C force. Either the C force would be above the neutral axis, or C force would be below the neutral axis. So there are two different possibilities of that C. So correspondingly, I would say let's try to solve for those two conditions. So what does this current point means? We are going to take that here. So we are solving because of the loads. One is your P, one is your E, one is your dead load, one is your live load. All those effects we are calculating, and we got some final stress diagram. This is your final stress diagram, and we want to see where is your resultant C force acting. So there are two different possibilities. Either it can be above the neutral axis or it can be below the neutral axis. Now I would say, let's try to make a mahal. Let's say that your C is acting somewhere here at some location of, let's call this part as E top. I would call it as E top, and this part I would call as E bottom. I would call this one as E bottom. Now once we say, do you know that strength concept? Once we know that our C force is somewhere here, can you calculate then finally that those stresses on that what you call as on that section? I would say one of the stresses is C by A, and one more stress is there because it's a sagging moment, so it would cause top compressive, bottom tensile, plus minus. So this would be CE, because we are calculating for E top, so we write the EC as E top for this case. So I would write this part as eccentricity as E top. So accordingly I can get that CE top by Z. CE top by Z. So I would say this is our condition. Now this is our final condition. I want that that stresses should be, I want no tension anywhere. I don't want any tension. I don't want tension. I want tensile stresses, tensile to be 0. I want tensile stresses to be 0. So what is the condition? Which of these do you think, where is the tensile stresses that can develop? That is the resultant. I would say at the top there is positive. So at the top there would be some positive value. Okay. At the bottom there is some one value is C by A positive, and one value is C by CET by Z, that's negative. So there's the chance that this value could be negative. So but the condition is that I want it to be 0. I want stress here to be 0. This is the condition here. I want tensile stress to be 0. I don't want any tensile stress here. I don't want any tensile stress. That means this one should be greater than or equal to 0. So this part should be either greater than or equal to 0. So the condition is there. F bottom, if I calculate the F bottom, that is C by A, then we have minus CET by Z. That should not be less than 0, or I can say that should be greater than or equal to 0. That should be greater than or equal to 0. So if it's talk about that cross section, we have this B and D. So I would say C by BD it should be greater than or equal to C ET by BD squared by 6. BD squared by 6. BD squared by 6. So this is the condition that your what you call as eccentricity, E top, I can say E top should be less than or equal to this would be equals to D by 6. Is it D by 6? So it should be less than or equal to D by 6. ET should be less than or equal to D by 6. And one more condition is there. If the resultant was below the neutral axis, if the resultant was below the neutral axis, let's say the section was somewhere here. Let's take the section here. This was your section, and C force came out to be somewhere here at some eccentricity of EB. So our stresses would be final. That's your C by A, and after that, because of the hogging, so I would say top tensile, bottom compressive, top tensile, bottom compressive, top tensile, bottom compressive, and the top stress is CEB top, yeah, CEB by Z. So I want that. I don't want any tensile stress for this condition also. I don't want any tensile stress for this condition. So net value should be equals to that. Here the stress should be 0. That tensile stress should not be there, such that here I can say tensile stress should be 0. So here might be some value of positive, but I don't care about positive. I'm saying that I don't want any tensile stress. And for that condition, I can say top stresses at the top is equals to C by A positive and minus CEB by Z. And this should be either greater than 0 or it should be equal to 0. It should not be less than 0. That means it should not be negative tensile. So accordingly, I can say once more I can say that EB, that should be less than D by 6. So for the symmetric rectangular section, I got two different limits. That if this is your section of D depth, and this is your neutral axis, and I want that no tension anywhere. I want no tensile stress in any fiber. I want no tensile stress in any fiber. I want no tensile stress in any fiber. That means your C force location should be somewhere here. C force location should be somewhere here. That's this region is your region where if the load was such that, so I can say I can call this part as Kern distance. I can call this part as Kern distance. Let's see what that means. So this is your distance that we can call as dk. Let's write it as dk, Kern distance. So this is the distance. This is the distance if moment is applied, that is external moment is applied. If the moment external is applied such that resultant C force lies within this range. So there would be no tensile stress anywhere. There would be no tensile stresses in the section. Tensile stresses in any fiber of the section, in any fiber of the section, cross section. So that we call as Kern distance, and that KD would be sum of E top plus E bottom. So that's your d by 6 plus d by 6. So your current distance should be less than or equal to d by 6 plus d by 6. That's d by 3. KD should be less than or equal to d by 3. So if the resultant of that, that means if the resultant of all those loads and the C force that goes developed, if the C force resultant is somewhere in the middle part of that section, that means there would be no tensile stress in any fiber of that section. So that's your current distance. So similarly, let's take one more problem that we can understand further. Let's take one more problem that we can further understand what this concept is all about. So it says that we don't want any tensile stresses. I want no tensile stresses. Okay, no tensile stress to be there. So let's take a problem that post-tension beam is there. Post-tension pre-stress concrete beam, PSC beam is there, and beam is 18 meter. This is your 18-meter beam, and I would say there's live load also. Because of the live load, the moment that is 648 kilonewton meter, and because there is M30 concrete, there is 15% losses. There is 15% of loss of those pre-stress, and there is one more thing, that's initial pre-stress force at the transfer stage, that is 1600 kilonewton. And okay, and the cross section of the beam, let's have the cross section. Let's go for the cross section. This is 500, this is 200, then after that we have only 250. So this is your section. I would say this is your 250. This is 250, this is 500 top, and depth is same, 200 and 200. After that, this part is total 1000. That means this part is only 600. 1000 minus 4, that's 600. Depth of the web, and width of the web is 150. And it's also mentioned that neutral axis is somewhere from the top, that is at a location of, so this is our neutral axis. The location here is y top equals to 416.7, and this y bottom equals to that's 583.3 millimeters. And the moment of inertia about the neutral axis is also given. INA is also given that 2.552 10 to the power 10 mm power 4. Area of the cross section should also be given. Area of the cross section, that's we can solve. That's 240000 millimeter square. That's area of the cross section of the concrete. Now we need to say get the Kern levels for these conditions. For this condition, get the Kern level. Get Kern levels. That means the Kern distance KD. So for that, I would say we have two different possibilities. We have two different possibilities of that C force. Let's say if the C force was above the neutral axis, if the C force was above the neutral axis at some eccentricity of 80, and there was one more possibility of that if the C force was below the neutral axis at some eccentricity of E bottom. So for these two conditions, we can solve that part of the problem. I would say because of this one, you had some general section. We don't care about the section. You had some section. There's some neutral axis, and because of this condition, first condition, I would say the stresses would be equals to, one of the stress is equals to C by A, and one more stress is because of the CE top by, and because this is a positive moment, so it causes sagging moment. So top compressive, bottom tensile, top compressive, bottom tensile. So this is CET by Z. So we have to keep here Z bottom. Do we have to write here Z bottom because we are calculating for the bottom part, because I want that condition that stress should not be tensile, that stress should be 0. So I am calculating at the bottom part only. So for that I have to keep here Z bottom. So I'm going to calculate for that part only. So I would say your C by area of the cross section should be plus, I would write minus CET by Z bottom should be greater than 0 or equal to 0. So this is the condition, that for no tensile stress anywhere in the section, no tensile stress. And for that I can now say your ET should be less than Z bottom by area of the cross section. Can I say that your ET should be less than Z bottom by area of the cross section? And if I substitute the values of Z bottom and that area cross section, your Z bottom was I neutral axis by Y bottom. I neutral axis was given to you 2.55 to 10 to the power 10 millimeter power 4, and divided by that Y bottom was also calculated as 583.3 millimeters. This one is your Y bottom. We already calculated those. This is Y bottom, this is Y top, and this is your INA neutral axis, and area of the cross section is 244 times 0. 244 times 0. So we can also solve it by that. If I say that this is ET equals to I by A, and we have that value of Y also. So this is actually R square by Y. That's Y bottom. We can write here Y bottom. So that is that radius of gyration square divided by Y bottom. So this is your general equation for non-symmetric section. So you can keep this one as a as a note. Similarly, your E bottom would be I by A, but Y top. So that's also R square by Y top. So that's one more condition we can have. So let's try to get that second condition. I would say there is some cross section we have some general cross section, and because of this, if the C force was below the neutral axis, one of the stress would be C by A, and one of the stress would be top tensile, bottom compressive. And finally, I want that no tensile stress anywhere. That means at the top fiber, even at the top fiber, I want that tensile stress to be 0. There is the possibility that, so I would write C by A minus CE E bottom. This was your E bottom eccentricity by Z bottom. Is it Z bottom or Z top? Which of these we have to take, because we are talking about the top section, top fiber. So we have to write here Z top. That should be greater than or equal to 0. That means it should not be tensile. It should be either compressive or it can be critical 0 value. So I would say your E bottom should be less than or equal to Z top by A. Yeah, this should be condition, or we can write it as E bottom should be less than equals to I by A and Y top. So that's, I would say that's equals to R square by Y top. This is one more condition. So we need to solve these two values. Such that we can have the final current distance. So let's solve for the first case. That's what's the value of E top. So let's have the critical condition that E top equals to I neutral axis by A by Y bottom. So let's have those values. Yeah, this is we have already written. We have already written that, and that value we can say that is coming out to be equals to 182.2 millimeters, 182.2 millimeters, and second part is your that E bottom is equals to that moment of inertia was your 2.55 to 10 to the power 10 mm power 4 divided by the area of the cross section 240000 mm square, and y top. Your value of y top was given to you. Y top was here. We can see 416.7, 416.7, 416.7 millimeters. So your eccentricity from the bottom side can be that's 255.1. This is the the critical distances we have. So the one is your 255.1, then next one is that 182.2. Let's go for that section now. Let's go for that section now. So this was your section, and I would say let's erase that data. I would say you have to go, you have to apply moment, such that the resultant is within the current limits. It's within the current distance such that your C force, such that there's no tensile stresses in any fiber of the section. So from the calculations we say that y top and y bottom, or we can say E top and E bottom was calculated, and those values we have. E top was your 182.2, some value of 182.2. Let's say this was 182.2, and from the bottom side we had 255.1, some value of 255.1, such that this is your current distance of kd equals to sum of those two. That was your 182.2 plus 255.1, such that your sum is there equals to kd. So your C force, if it's passing in this range, that means you would be having no tensile stresses in any of the fiber of the cross section. So final conclusion is that there's only compressive stress throughout. Stress is compressive throughout the section. Stress is compressive throughout the section. Indirectly it means stress is compressive throughout the section. If there is no tensile stress, that means compressive would be always. All the fibers will be having current, that compressive stress. Okay, thank you for watching that topic, that's cracking moment and current points related to that. Thank you for watching that. Thank you.